Okay. So this chapter 9 is all about like dealing with three-dimensional figures. I would say considerably easier than the vector chapter that we just finished. As far as the calculation that's involved here, it's all fairly straightforward, like right triangle geometry things, or just applying formulas, which I will provide. So is not a very difficult in that, from a calculation perspective. Usually the most challenging part of this chapter for students is the visualization, because you're talking about thinking about something in three-dimensional space. And that's kind of what this first couple of sections are going to be kind of concerned with. So in this first section, what we're going to be looking at is finding the length of a segment inside of a three-dimensional figure. So to do this, what we're going to be interested in doing is being able to find what are called a calculation triangle. Now, preferably, we'd like those calculation triangles to be right triangles, because those are much easier to deal with, as we have lots of very powerful tools that we can use to calculate the side lengths inside of a right triangle that don't really work for non-right triangles. Probably somebody can grab the light for us. It's probably bright enough outside that we don't need those on right now. Thanks, Bridge. So, for example, if we have a pyramid like this, this is an example of a calculation triangle. So here in pink. Is this the only calculation triangle that we might need in here? No, depending on what the information we're given or what we're being asked to find, there could be several different calculation triangles that might be of interest to us in something like this pyramid. One of the skills that we'll have to develop during the course of this chapter is being able to pick out which calculation triangles are of interest to us and which are not. So that's a fairly obvious calculation triangle. We can have some that are maybe a little bit less obvious to think about. So for example, in this cuboid, again, a cuboid is just another term for something like a box, where the sides of the box are rectangles. So this pink triangle is just like half of the front of the box, right? That's a pretty obvious, easy to see calculation triangle. This blue triangle is also a right triangle. A little bit harder to see that that's a right triangle. So one side of that triangle is like the back top edge of the box. The other side is a diagonal on the side of the box. And this third side is like the internal diagonal that goes from the back left corner of our box to the lower front corner of the box, front right corner of the box. But that's still a right triangle. And the way I know that that's still a right triangle is I know that this side FG intersects this face, this plane GHDC, at a right angle, right? Everybody agree with that? So because GD is inside of that plane, it's part of that face, I know it's going to be at a right angle there. And maybe that's not easy to see right away or easy to identify that that's a right triangle, or that even that might be a useful triangle. But that's what I mean by this is maybe the hardest part about this chapter, is being able to look at one of these figures in space and go, okay, what right triangle can I find in here? And part of what we're doing today is just kind of building up some intuition and showing you some of these maybe not super obvious right triangle situations, so that you, when you get to trying some of these things in the homework, have a better understanding of where I can be looking. You know what I mean? Okay. And so those are the two right triangles there. So another example, again, the pink triangle is probably obvious. This is a triangular prism. Notice this isn't a pyramid because it doesn't have like just one point at the top. The pink triangle is probably obvious, right? That's just half of one of these rectangular sides. The blue one's a little harder to see, but you'll see that BG is like the height of one of these triangular faces. BE is like that edge of where the rectangular faces meet. And I know that that is at a right angle because I know that this edge BE intersects the triangle at a right angle. That plane that the triangle lives in anyway is at a right angle. And then EG is like inside of this prism, right? It's going from the point at the back down to the base of that triangle at the front. The midpoint of the base even. As it surely looks like this is an isosceles triangle here. Everybody okay there? So again, no calculation that we're doing right now. We're just trying to build up some intuition about finding these calculation triangles on our own so that we're able to have a better idea of like where to look for these things. So here's another one. Now I would think that both of these are not super obvious calculation triangles. So if I look at the square pyramid here, we say it's a square pyramid because the base of the pyramid is a square. So one right triangle is this triangle EFM, where M is the midpoint of one of the sides of this square pyramid. So FM is along the base of my pyramid. EF is the height of the pyramid. And then EM, this length here is called a slant length, where it's going down. It's like the height of that triangular face on the pyramid. Everybody okay there? Again, I know that this is a right triangle because the height of my pyramid is going to be perpendicular to the base of the triangle. So I know that that's a right angle. The pink one is also a right triangle, although it's a little bit less obvious. It certainly doesn't look like a right triangle the way it's drawn with perspective here. But again, I know that EF is a height for my pyramid, and AF is inside the base of the pyramid, and I know that the height intersects the base at a right angle. So I know that that's also a right triangle, even though it doesn't really look like it in the drawing. I know that it is one. And then this side, AE, is like an edge length for this pyramid. Is the slant length and this edge length going to be the same? What do you guys think? They are decidedly different. There's no circumstance in which those will be the same length. Anyways, and those are the two triangles. Oftentimes it's helpful to draw them on the side once you've kind of identified them so that it's easy to draw in the lengths and your picture doesn't get too busy. Okay, you ready to try some examples here? Okay. So we have a shoebox that's 32 centimeters long, 18 centimeters wide, and 11 centimeters high. We want to calculate the length of the longest rod that'll fit inside the box. So we have some box, right? How can we fit? What's going to be the way to fit the longest possible object inside of that? So use some imagination, like close your eyes if you need to. Think about what a shoebox looks like. And if you're trying to fit like a stick or something in there, how would you put that stick so that you can get the longest possible stick in there? Ben? Okay. Diagonally from opposite corners. When you say opposite corners, what do you mean there?
The lowest, like the lower corner on one side and the higher corner on the other side.
Excellent. Yeah. So Ben says that to do this, we're needing our stick to go from like A to G, right? Where we have the lower corner in the front to an upper corner in the back. Everybody see that? That's going to be the longest possible thing we could fit inside of our shoebox. So my first step is to kind of draw in a picture, like what we've done here, and identify a calculation triangle. So the calculation triangle that I've identified here is this one AGC. It's the only right triangle that's going to include that side AG. Right? Is everybody okay with how I've drawn this in? Okay. How many sides of this triangle ACG do we know? It wouldn't be much of a question if we knew all three sides.
We know two, but
We really only know one. All we know is GC, right?
Don't you know AC though because of the Pythagorean?
Well, we can calculate the length for AC. Yes, it's calculable. We don't know it though right from just the given information. So you're correct. We can find AC by solving for AC. What triangle am I going to use to solve for AC there, Sam? So Sam says to use ADC here, which is great. That's a right triangle. How do we know that's a right triangle? Because AD and DC are at a right angle because it's part of a rectangle, right? Everybody agree with that? Okay. So, and Sam suggests we can use the Pythagorean theorem to solve for this other side. So that's easy, right? And now once we have this, we have enough information to solve for a GC, right? Because now we have two of the three sides and we can use the Pythagorean theorem again. Is everybody okay with that idea? So there's my new triangle. Notice I used the decimal approximation there for AC. That's where the 36.7 comes from. And just doing the Pythagorean theorem again, I get that. Let's look at another example. EABCD is a square-based right triangle, or right pyramid, excuse me, with sides of 12 centimeters, and the height of the pyramid is 9.5 centimeters. The first thing we want to do is calculate the length of EC. So I'd start by drawing a picture and identifying a calculation triangle that I can use. So here's my right pyramid. And the calculation triangle I found here is EFC. Notice that I know this is a right triangle because the height of my pyramid intersects the base at a 90-degree angle. How many sides of this triangle do I know? Just one, right? I just know the height. So I'm also going to have to solve for which other side before I can get EC? I also need FC, right? So what other calculation triangle can I use for FC? How about ADC? Is that okay with everybody? Notice that FC is not actually a side length of this second calculation triangle. How am I going to get FC from this? Can I just take AC and divide by 2? Why is it okay to do that? Because this is a square pyramid. If this was not a square pyramid, that might not necessarily be at the intersection of the diagonals there. But that's an old geometry theorem, right? That for a parallelogram, the diagonals bisect each other. Everybody remember that? Maybe not. It was a long time ago. There's going to be a lot of those little geometry theorems that I'm going to use to justify things. Now, it's not critical that you kind of remember them, but it helps a little bit to justify things like that, of why it's okay for me to just divide this by 2. Okay? You probably would have thought to do that because it looks like you can do that. But it's worth mentioning. So here's my drawing of my first calculation triangle for ADC. So I calculated AC, and then I had to divide that by 2. Everybody okay with that? Now that we have FC, we have enough to solve for EC. Everybody's okay there? So when we do that, we get 12.7. Again, just using the Pythagorean theorem again. Now, as in a little aside here, say that are these problems possible to do if you didn't use right triangles and didn't use the Pythagorean theorem? We could use the law of sines and cosines, but to use those, what do we also need to have? We need to have at least one angle measure to use one of those, right? So on a problem like this where we're given no angle measures, it's usually a good sign that you should be looking expressly for, right triangles to use the Pythagorean theorem for. In a problem where you are given some angle measures, the law of sines and cosines might be a viable option, although it may still be possible to do with, like several reference triangles and still use the right triangles to do this. Okay. Question B says M is the midpoint on one of these sides, and we want to calculate the length of EM. So again, I drew in my little calculation triangle. So we know EF, right? That's the height. We're looking for EM. Do we have enough information to find FM? You don't even need to draw a calculation triangle for that. What's the length for FM? 6. How do I know it's 6? The side lengths are 12. F is the center of the square at the base, so it's got to be half of 6, or half of 12. So there's that, and we do the Pythagorean theorem again, and boom. There's my answer. Is everybody happy there? So again, not so bad, right? Considerably easier than what we just got done doing by a large margin. Now, again, the tricky part about these is finding the calculation triangle that you're going to need to use, because there's lots of them floating around in there. And sometimes there's not going to be just one that you need. We've seen several examples here where we had to use kind of 2 of them. And then part C says, why is length of EC not the same as EM? Well, they're definitely different segments, right? So, for example, a decent answer would be, if we take a triangle that includes EM and EC, it might be the triangle EMC. Everybody agree with that? Yes? That's a right triangle, correct? Because EM is a height for the triangular face there, which makes EC the hypotenuse for that right triangle, which has to be the longest side. It can't be equal to another. So, again, to help justify that to you. But again, these are, EC is the, is the edge, the slant edge, and EM is this vertical height for that triangle EDC. So it's the height of the face. Okay, let's look at another example here. If AB is 11.3 and the angle, this is a symbol for angle that's sometimes used, is for ABC is 53 degrees, we want to calculate the radius of this cone. So I'm going to use the reference triangle that I've drawn in here, BDC. What do we know here? What information can I fill into this triangle BDC? What's the length of BC? 11.3. Everybody agree with that? What's the angle for DBC? $26.5? Okay. Why is that okay? Why can't I just divide that angle measure by 2? Can I always do that? Not only do I need to know that it's a right angle here, I need something else. If I look at this triangle ABC, what kind of triangle is this? Has a special name for this kind of a triangle. I heard somebody whisper it quiet. Isosceles. What is an isosceles triangle again? 2 side lengths are the same, right? In an isosceles triangle, if you look at this apex angle, the angle between the 2 identical sides, if you draw a perpendicular bisector there, or the altitude drawn from that angle, that's an angle bisector. It also bisects this side length. This is true only for isosceles triangles. Okay, so if this was not an isosceles triangle, you cannot just say, oh, that thing's an angle bisector divided by 2. You need to know that it's an isosceles triangle. Again, that's an old geometry theorem. I don't expect you to remember it offhand, but that's why we're talking about it now, right? To remind you. As that's one that students very much love to just draw that line down, it divides everything in half. Oh, no. Only if it's an isosceles triangle can you do that. Okay. So we have this information, right? How are we going to solve for that side R? This is way back to the very beginning of first semester and back into your geometry class. SOHCAHTOA? Yeah, we're going to use sine. We have a right triangle. I can just say sine of 26.5 is opposite over hypotenuse. Oops. So when I multiply both sides by 11.3, I get R is 504. What do you guys think? This is should be, the calculation-wise, pretty easy, right? Especially in comparison to what we've just gotten done. So everybody's in for a nice little relief here from the last chapter, which was very conceptually difficult, to something that's much more familiar, calculation-wise, much simpler to do the calculations here. Notice in this section, we did nothing other than Pythagorean theorems and like SOHCAHTOA. Should be things that we're very comfortable doing. Okay? Okay. The next section, we're doing the same thing, except here we're looking for angle measures instead of side lengths. But the approach is going to be the same. We're going to find calculation triangles, preferably right triangles, and then use SOHCAHTOA and our inverses for sine, cosine, and tangent to determine angle measures, right? So it's almost the same kind of problems, the same approach. So one thing worth noting here is that if I have a line BC that's in this plane, the angle formed here with the surface is going to be the same as the angle from AB to this line BC that's in the plane. It doesn't really matter where this line BC is going. As long as it's in the plane, it's fine. So just worth pointing out. So for example, if I want this angle ABC, this angle B is really with the side AB and the base of this cone. Everybody okay there? So these are examples of like calculation triangles I might draw in order to find like a given angle measure. Okay. So let's look at an example here. So for the triangular prism, we're going to first calculate the height of that prism by finding the side EB. And then we're going to find the length of DB. And then we're going to find the length of DE. And then we're going to find this angle EDB. Okay with that plan? So, how am I going to calculate EB? Which triangle would I use to do that? How about AEB? That look good to you guys? So clearly this side is, or this angle is 21 degrees, right? What other piece of information do I know here? For AEB? AB is also 15. So there's that. How can I find EB? Going to use SOHCAHTOA. Which one would I use? Tangent. So I want opposite over adjacent. So there's my length for EB. Everybody happy there? Which triangle do we want to use to calculate the length of BD? About like BDC or ABD, it doesn't really matter. They're both kind of the same triangle. So let's say we're looking at BDC. Obviously, DC is 15. What other side do I know? BC is 23, right? And so I can use the Pythagorean theorem to find BD. Everybody good there? Right? Now I know BD and I know EB. To find DE, I can use the Pythagorean theorem again, right? So the next thing we were looking for was DE. So I just took my previous two answers and then used the Pythagorean theorem again. Everybody okay there? Good. And the last thing that it wanted this angle EDB, right? So because I know all three sides of this triangle, does it matter which trig function I use? No. I could use any one of them, right? So for the sake of argument, I use tangent. So I say that tangent inverse is equal to EB over BD, which was 11.8-ish degrees. So again, is this really any harder than what we just got done doing? No, it's really like the same as the last section, right? So another example. We have a cylindrical drum that contains this stick that's fit in there diagonally. First thing we ask for is the length of the stick. How would I do that? Yeah, I can just use the triangle ABC and use the Pythagorean theorem straight out. Because what's the length of AC gotta be? Yeah, 2 times the 5.8. So there's that. No big deal there. And then if I wanted the angle that the stick makes with the side of the drum, which angle am I looking for? I want ABC, right? I want this angle up here. Everybody agree that that's the angle the stick is making with the side of the drum? So there's my information. Do I have enough? Okay, what am I going to use to find that angle? Tangent. So I can say tangent of that angle is 11.6 over 15.8. And when I do tan inverse to both sides, I get 36 and change. Everybody cool there? So very simple calculation-wise, right? We're not doing anything complicated, right? Again, the hardest part, the trickiest part is getting the triangles that you need out of the picture. I think this is the last example here. So we have a rescue helicopter, and it's shining a spotlight down on something. And we're looking for the angle here at the apex of the cone. So I want LMO. Everybody okay there? Okay. So I know that the diameter is 140. So what I'm going to do is I'm going to make the calculation triangle LNM. And because the triangle LMO is isosceles, I can just calculate this angle up here and multiply it by 2 to get the whole thing. Everybody good with that plan? So there is my calculation triangle. How am I going to calculate this angle M? Using which trig function? Tangent. So when I do that, I get 24 point whatever. And then to get the apex angle, I just need to multiply that by 2. And I'm done. Everybody feel okay here? So again, these shouldn't be too terribly challenging.